Hello guys, today we are going to start the next chapter, which is chapter 16. This chapter is about kinematics and mainly vector kinematics. Alright, if you guys remember from one of our last lectures is when we discussed the fact that every point on a rigid body could have a different velocity, right? So we're gonna start looking into rigid bodies. So this is some random rigid body, and every point on this rigid body actually will have a different velocity unless this object is translating. If this object is translating, then we know all these velocities are going to be the same, right? However, if this guy is translating and also rotating, and what we're gonna define rotation as angular velocity, then these points will have different velocities. So the goal of this chapter is to basically find the velocity, or to relate the velocities between any two points. All right. Here's what we're gonna do this. So what I want to do is we can simply draw a frame, right? This is a frame and this is your rigid body. Usually for you to be able to get the velocity of any point on a rigid body, you need to know the velocity vector of one point, right? So every point here will have a different velocity. So I'm gonna take this point O, right? And my goal is to really find the velocity at point P. Alright, so this is the velocity, this is point P, and then this is point O, and obviously these two will have different velocities. So I'm trying to find the velocity of point P in terms of the velocity of point O. So let me do something. So what I'll do is I'm gonna call this RO, right, which is a vector basically from point, from the origin, right? Let's just call it a prime so that it's not this point. And this is my X and Y plane. And this is my RP. All right, this is a vector RP, and this vector from P to O, I can actually call this as RPO, and then this is the relative difference between point P and then point O. What I do know is that well, you know, the velocity of point O, right, is going to be equal to what? Is going to be equal to dRO over dt, right? So the rate of change of this vector with respect to time will give me VO, and VO here basically, I'm gonna actually draw it as separate. This could be VO, right? This could be VO. VO is the derivative of this velocity vector. So at that instant of time, the velocity vector is going to go like here, for example, right? And then it's gonna give you this velocity vector. Okay, so I can technically write my position vector RP, right, as RO plus RP with respect to O. So the position of point P is equal to the position of point O, or the vector, right? So this vector is equal to this vector plus this vector. You know, this is called the vector loop equation, right? So RP is equal to RO plus RPO. Basically, simply adding these two vectors in geometry. This vector will have an X and Y components. This vector will have X and Y components. By adding the X components of these two vectors, I'm going to end up with the same X component of this vector. And by adding the Y components of these two vectors, I'm also going to end up as the same Y position of this vector. The same thing basically applies for 2 dimensions. However, in this course, we are only going to be dealing with planar kinematics, mainly bodies that basically are moving in this plane, or on the board, for example, you know, objects that like rotate, things like that, etc. Okay, now if I'm trying to get the velocity of point P, how do I get the velocity of point P? I'm going to differentiate that expression, and then if I say that the velocity of point P is going to be equal to drp over dt is going to be equal to, I'm going to differentiate this, and here you know that this is going to be VO, right, the velocity of point O based on that relationship, plus the differentiation of RPO with respect to dt. Alright, now this vector has to be an absolute vector, right? So this vector is measured, so the components of these vectors, the X and Y components, are always measured with respect to this X and Y frame, or I and J frame. Alright, and there's one more property that this rigid body will have. So Guys, pay attention to this very well because this is extremely important that you understand. So every rigid body basically will have an angular velocity and it will also have an angular acceleration, and then both of those are actually vectors. So I'm going to call this guy is my omega. Every rigid body will have one omega, one angular velocity, all right? And the angular velocity is the velocity or the change of an angle of a line. So the angular velocity basically describe the rotation of a line. A point cannot have an angular velocity, so things that will have angular velocity are objects, right? Or like this pen will have an angular velocity, right? This mouse will have an angular velocity, right? And then each point on the mouse will have a different velocity, so on and so forth, all right? All right, so here I'm at Vp is equal to Vo plus drpo dt, and now I'm looking at how that vector is changing, all right? So here's what we're going to introduce. Vo will be the same, but the derivative of a vector, this vector is being rotated by this angular velocity. So you can quickly imagine that this vector, I'm going to actually draw it over here, right? This is your RPO, and if I want to see the time change of this vector, like where is that vector after an instant time t plus dt, and that vector is being rotated by omega, so you can quickly imagine that as a result of this rotation, this vector is going to be rotated like that, right? And this component right there is actually equal to d theta, right? As a function of that, ultimately this is going to be actually equal to omega cross RPO. And here's what, so omega is actually a vector, angular velocity is a vector, but this vector is going to be perpendicular to the plane of rotation. So omega is going to be a vector like that, pointing toward up. So in the rotation of omega, then this is going to be my vector, and this vector omega cross r, it's going to give me this vector omega cross RPO, and that will actually be the velocity. All right, so just remember that. So VO plus omega, right, cross RPO, and this will actually, this component will give me the contribution of the angular rotation. So the velocity of point P on the rigid body, if this object is not rotating, then omega is 0, then the velocity of any point on that rigid body will be equal to VO. So if VO is like that and the rigid body is not rotating, then I know this whole thing is going to be translating along VO, right? But if I have omega, if VO is 0, for example, if point O has no velocity, that this part would be 0, then the velocity of any point is going to be equal omega cross RPO. It's like this rigid body would be rotating about point O, and you would only use this relationship. All right. There's one more thing that we are going to add here is that this is the velocity of any point on a rigid body, right? So this is that, in that case, point P is actually a point in that rigid, just like an atom in that rigid body. However, point P could actually be moving on that rigid body, right? In that case, like let's say you have a bug, right, that is sitting on that rigid body, and even though the rigid body is not rotating and the velocity of point O is not moving, so that rigid body is right there. So you would still need to actually incorporate the velocity of point P, because point P itself could be trying to walk on that rigid body, right? Let's say it was a bug. So I'm going to add this last term, and this last term only is the relative velocity, and usually we refer to it as like this. We have like a tiny smaller frame. Ultimately, when you add all these velocity vectors, you have to sum all these vectors in the same frame. Sometimes, on assignments they would give you like a frame on the rigid body. You can totally use that, but you cannot add vectors in two different frames, right? You have to convert the vector, right? So let's say this is point P. Point P could actually have a velocity on its own. Like point P could be like a bug, right? That is actually moving on this rigid body, and in that case you would need to add these contributions. Again, ultimately, when you are adding all these vectors have to be in the same frame. Okay guys, so this is how you find the velocity of any point on the rigid body, and this relationship always relate the velocities of 2 points, right? You need to know the velocity of one point, and you need to know the angular velocity of the rigid body in order for you to be able to find the velocity of any other point on that rigid body. So this relationship basically can relate the velocities of 2 points. All right. regarding this portion, right, why is drp/dt equal to this, right? We said that drpo, so I'm gonna actually write that in a separate figure where I wanna show you this derivative and how this derivative basically work. So if you have a vector, right, and then we call this RPO, and I would like you guys to be very careful. RPO is a vector that points from point O to point P always. So vector of point P relative to O. So you always need to be careful about the direction of this vector. So what is TRPO? And then we said this vector could be rotated by an angular velocity omega, and then omega obviously is a vector like that, right? So as a result of this, this is your omega cross RPO. It's going to give you this direction of the velocity. So d RPO over dt, all right, it's going to be equal to what? So as a result of this omega, what is that omega? Omega is the velocity or the angular velocity which is spinning that vector, and we know this portion is going to be here d theta, right? And we know this length right there, I'm not going to put a vector on it, this length is going to be equal to what? RPO, right, multiplied by d theta. That is the length of this. If you want to get the actual velocity, you are going to differentiate that length with respect to time, right? And again here, we also, not only we need the velocity, we also need the direction. So drpo dt is going to be equal to, what is the derivative of this length, right? This length is going to be RPO times d theta. So derivative of this is going to be RPO, right, d theta over dt, which is theta prime, right? So RPO times d theta over dt, it's going to be RPO times theta prime, but I still need to know a vector, right? So how would that vector look like? That vector is going to be along this direction, right? So how do you get this direction? So instead of doing RPO times theta prime, you can directly do omega cross RPO. So this actually is the derivative itself, and also it gives you the direction, right? So omega cross RPO. So omega, right? So take the right hand rule. So this is the rotation of your thumb or rotation of your fist. Omega cross RPO, right? So this is omega cross RPO. It's going to give you this direction, which is along this. So this is your velocity vector contribution due to omega. Okay, drpo dt is going to always be equal to that. So every time you differentiate a vector, you would actually add omega cross RPO, and if that point itself, so this component is only caused by the rotation, right? If that point P is also moving, then you would always have to add. So I'm gonna write it, drpo over dt will always be equal to omega cross RPO. Again, this is when you are differentiating a vector that is rotating, right? This derivative here is only the velocity of this vector along the direction which is perpendicular to that vector. You still need to incorporate the other contributions, which is Vp with respect to O in a smaller frame, which is basically the relative velocity. All right, so that is, guys, very important. Okay, and then more importantly is obviously this relationship. All right, so this is how basically we can find the velocity of any point. And the best way would be to go from here is to start doing some examples, and I think you will really learn it the best by doing examples.